Let's get started. So today I'm going to go over, I think most of you were at the presentation at Bechtel or the mock kickoff. But who was at the mock kickoff? You were? You guys were, which of you were at the Bechtel one?
I think I was there.
I think
It
you
was
went for a
kind of-
little while, yeah.
Yeah. So did you see this electrical presentation or were you part of something else?
I don't remember seeing the electrical presentation.
Okay. So I'm not going to go through all the gory details again, but it is posted on the internet, and I sent a link out to where you can find it, so I'll send you a link to that
No, we
again.
got it, we got it.
Okay.
I think you sent it already,
Okay.
yeah.
So
That's the PowerPoint presentation?
Yeah.
Yeah,
Yeah. So that was the latest version. So that was essentially what was presented at Bechtel. So I'm going to focus more on what the functionality of the parts are, and we'll do the hands-on. Like the other one, there was just way too many people. Here, we probably have enough that everybody can do it without having to. You do it, and then you pass it to you, and so you can all do it at the same time. See how this works. So this is an overall view of the system. The RoboRio is a small microcomputer that controls everything, and when you go and write software, it gets compiled into the code that the processor and that thing wants to see, and it gets downloaded, I think, through one of the USB ports. The software guys, they're going to take care of that. So if you're doing electrical stuff, don't worry about it. But it's got a number of different ports. It can connect up to different digital sensors. It'll connect to, it's got some PWM outputs for controlling things like your motor controllers or spike relays. In this system, you're connected to a 12-volt battery, ultimately. So the power comes in through a circuit breaker onto this power distribution board, and there's self-resetting circuit breakers that go out to different circuits. So from here, it can go out to a motor controller to a motor. Well, if you just connect the motor onto 12 volts, it runs at full power, 100%. You've done FLL, so that's like saying 100%, 0 or 100%. That's useful, but it isn't. Sometimes, a lot of the time, you don't want 0 and you don't want 100%. You want something in between. So what PWM, pulse width modulation, is if you go and pulse the connection to 12 volts, there's also, it's not really very clear in these pictures, but there's also some analog sensors that can be put in here. So certain types of light sensors, you can use a potentiometer, which is like a volume control in your radio. Say you've got an arm that's going up and down, you can put one right at the joint. And so as it's going up and down, it's like you turning the knob, and you hook it up the right way, and you can read what position that arm is at. You can also hook up what's called an encoder. And that's a thing where there's a disc with a whole bunch of lines on it, and as you rotate it, there's a light sensor that senses the lines going by. And so, those, I think, come in the digital I/O, and then this port here is for controlling the relays. So that's the RoboRio. It's got a couple USB ports. That's the USB-B port. And that's an Ethernet port that goes to the camera and goes to the radio and stuff. Oh no, the bridge now goes into USB. And then there's what's called a CAN bus, C-A-N. CAN stands for Control Area Network. It was originally developed for cars. It's kind of like USB, but different. It's like your USB in that it's a serial. The data is going to sent all sent down a pair of wires. Instead of, okay, PWM, each one of these gets a set of wires on one of these ports. CAN, I think you can go to like 256 nodes, something like that. And they're just daisy chained. So if you follow this through, it goes from this port to one port on here, and then it just comes back out, goes, so there's an in and out. And it just daisy chains through to here, comes through to this guy. And you just keep going and going and going and going. So that makes for the wiring, you know, like in, so with this, like I said, you got wire, if these things were located far away, you're going to have power wires running out to these, and you're going to have these control cables running out to every one. With these, if these guys are located far away from this, you still just have this one pair of wires going to this. There's a short one joining these two, and then something going on to the next guy. So the wiring is a lot nicer. There's a lot less stuff flying absolutely everywhere. And if you look at last year's robot, you'll see that. So let's see, that's kind of part of the system. So the motor controllers are how we control the motors, and that's how we get the physical action that we want in the robot. Some other functions, the information from the driver station goes into a little laptop or netbook and gets sent through a Wi-Fi connection. And that's why you're prohibited from using Wi-Fi specifically, especially at these tournaments, because you're going to compete. There's only so many channels in a Wi-Fi system, and so it's received by this bridge, which is itself a Wi-Fi router, and so each robot is assigned a unique identification. There's a dedicated connection to this voltage regulator module, because the voltage on the battery will fluctuate quite dramatically depending on the load on the system. Like if you remember the year with the big round ball, we had about 3.5 horsepower worth of motors. And when you accelerate it hard, I don't know what the voltage went to, but it won't be 12 volts. It won't be anything close. It can go as low as 8 volts. And some of the other equipment won't like the fluctuations. Also, some stuff don't want 12 volts. Some of them want 5 volts. So this little box here converts the 12 volts to stable 5 volts. I don't recall if it made 12. And you can connect up things like the cameras to it. Because some of this stuff, if the voltage fluctuates, the power supply voltage fluctuates too much, what comes out of them gets messed up in different ways. This is the pneumatic control module. This is an instance where the CAN bus makes a lot of sense. There's actually, I think there's 8 channels on this. So there's 8 sets of outputs, where one set of outputs you connect it to what's called a solenoid. The solenoid is an air control valve that is controlled electrically. So there's a little electromagnet. When you energize it, it flips the switch one way, and then when you don't energize it, you de-energize it, it goes back to the other state. So you can connect your air supply into one end of this, and then the air will come out, and by changing whether there's power here or not, then you turn on or off the airflow coming out of this. And this thing, each one of these 8 outputs has an address, and you say, oh, PCM output 1, turn on, turn off, or whatever, and then PCM output 4, turn on, turn off, whatever state. And it's all done through this one pair of wires. So the wiring is way, way nicer with the CAN bus. It does mean if you break those wires, you lose everything, but it's not that hard to go and protect it. It's not, that's also why I'm doing this electrical training, because in the past, I know Awtybots has had, and a lot of other teams have had problems with connections, but in the last 2 years, I think we had one bad electrical connection that was a battery wire that was crimped like years ago. And it's not hard, okay, to have a good connection. And other teams have done the same thing too. So it's kind of, the CAN bus is good and bad in that it makes it all or nothing, but it's not that hard to make it all good. The CAN bus also comes back into the power distribution board, and what that function is it has circuitry to monitor the current in all of these channels, so that you know, so you have a circuit breaker here, so if you go to some crazy current, you can cut it off. I was going to go into talking about how you lay out stuff. There's a number of different, you have all those parts. One thing you can do is just kind of go, oh, this fits here, this fits here, this fits here, and that's what often happens on FRC teams. There's the CAD guy, if there is one. They go and put this stuff down. Okay, go wire it. And we go back to that drawing. One of the rules is from the battery you must go to the circuit breaker and then it goes to here. Well, if they put this way buried at one end of the robot and they put this way at the other end of the robot, and this is supposed to be accessible because this acts as the master on-off switch, and they've gone and put this like way off in another place, you're going to have big thick wiring running all over the place. Okay? And then if they put, say these are the motors driving one side of your robot, and they've put these on the other side. Okay, that, you can imagine that makes things really stupid. Okay? Just to let you know, you don't need to feel bad. They do that where I work too. Okay? And these are people who are paid to do this. So that's why I talk about layout. You have mechanical constraints. Like obviously the parts have to fit where you're trying to put them. Sorry? Yeah. And then, well, sometimes we make room. Like if that is the best place to put something, it must absolutely go there. Like say the circuit breaker must be accessible. The stuff I work on, sometimes the customer wants this thing, whatever it is, in this location. So we'll rearrange the other stuff around it to make room for it, because they absolutely need it there for whatever reason. Document what you've done, because when you're not, say you built it, but you're not there and he needs to fix it, what is this? Okay. This motor isn't running. Where's the motor controller for it? Especially if it's all mixed up. You can imagine it'd be a real mess. Okay. And then you want to consider the power flow. So like I gave a really negative example where you've got the power distribution panel, the battery, and the breaker just all over the place. Typically, they're located very close to each other. You can trace it from the battery to the breaker through just about that much wire and then into the power distribution panel almost right away. Okay, and you can see where everything flows. And from the power distribution panel, it comes out and then goes to the motor controllers and then to the motors. Often they have motors on both sides of the robot. You would locate the motor controllers for the motors on that side, right? and then signal flow. Like especially when you're using PWM connections, every single motor controller has a set of wires running back to the Robo-Rio. So you want to be a little conscious of that, but those wires are much smaller, so they're easier to run all over the place. There's also the issue of weight. The power wires are the 12 thick power wires are quite heavy. Like this stuff, that's a reasonable amount of weight. Okay, so each connection, you've got two wires, one going out, one coming back. Like last year, I don't know if you remember, Rachel, you were on the team? Do you remember there was some weekends we had hole saws?
Yeah.
We gained about 2 pounds with all that work. That's a good portion of a pound. Okay, so if you lay it out so you got to run wires really far, you're going to add weight, okay? And it's going to be really hard to get that weight out. Manufacturability and serviceability. I reached in with my hand and okay, let's start with something basic. The two power wires running to their main controller, it wasn't a Robo-Rio that year, it was the equivalent. I reached in, put my fingers on it, and just went like this. It was way deep, so I wasn't pulling on it, and the two wires popped out. Okay, that's pretty simple to fix. We need to just tighten the screws that hold those wires in. Well, it took half an hour of taking all kinds of other stuff off to get at it. Like I said, I was only able to reach my finger in. So there was no way we were going to be able to put screwdrivers in or anything. We had to take off this top board with all these other parts, and so that was a case of very poor serviceability. Okay, and then you should review and iterate. So he was the student in charge of electrical, and then Seth was doing the CAD. The three of us on a Sunday went from middle of the afternoon around this time till about midnight. Well, I went to bed at midnight. Those guys kept going till about 3 in the morning. So Seth would make a layout, he'd email a PDF to Nathan and I, we'd go to our email every so often and, oh hey, Seth sent something. We'd go and pull it up on screen, look at it and go, this part of it's good, what if you move this and move that, and we'd write back to him. And he'd go and make some changes, go do some more homework, maybe, probably not. And then he'd send something back and we'd go around and around and around. And we got it refined real nice. So that's what I mean by review and iterate. So these are the PWM wires coming out this way for these guys. This bundle of wires down here are for the digital I/O for things like limit switches and such. And they went from the bottom, these connections right here that you can see on this side, the top side, which is really the bottom of the robot, are all the PWMs. On the other side of it are the digital I/O for your limit switches, and they got run and then bundle out this way, out through a hole into the space up here at the front of the robot. And that was really terrible, because how do you get to these things? You know, this thing is right up against these things. You can't reach into there. We had to make all these connections and then lower this in, and this was stuck onto this surface with Velcro also. So you're worrying about the stuff coming off, but even if it does come loose, there is nowhere for it to go. Okay, and I think these breakers, we actually put a little piece of pool noodle foam onto the plastic that kind of pressed on top, although these are pretty tight anyway. So I think that's why the inspector wanted the panel off, because the pool noodle foam covered these up. There's certain ratings for these that have to go in certain locations, and he couldn't read it. But here's an example of something not to do. That's just inaccessible. So serviceability is really poor. We never had to go and mess with it, but if we did, you could see that that's going to be a total pain in the butt. Building it was a real pain in the butt because this is all just a bit too tight. And so we had to dress these cables, and you can kind of see occasionally there's some black cable ties that bind it all together into this bundle. And it had to be all shaped into just the right shape. But that took a lot of work, okay? Now, one of the things I advocate is to have wiring channels. And so if you look at this, there's a channel through here and a channel through here, which I wish was a bit bigger. And then there's actually a channel out here and a channel out here. So the channel here, you get the control wires coming like this to each of the motor controllers. And through here, you got the digital I/O. The power wires just cross the channel, and then this channel out here is for the connections to the from the motor controllers to the motors. Somewhere, yeah, over here there's a spike relay that also went out to run the compressor. Now, one of the things that you should not do is run the control wires with the power wires, because I don't know if you've covered this in physics. When you have a current flowing in a wire, it causes a magnetic field. The magnetic, so PWM means that you're turning, the current will be fluctuating. When you have a fluctuating current in a wire, you will get a fluctuating magnetic field. Now, the converse also happens. If you have a fluctuating magnetic field in the vicinity of a wire, that will tend to cause a fluctuating current to flow. So you're controlling these things by injecting bits of current through these wires into the certain pins on certain connections on this. If you were to inject spurious currents into these wires, you could cause this to do stuff that you were not intending to do. Okay, and that's electrical interference. So they tell you, not to run signal wires and power wires together. But if you look at this, I have signal wires running this way and coming to all these, and I have power wires running across. Well, you can't always keep them apart, but what you can do is minimize the interference, and you do that by the coupling between the power wires and the signal wires is maximized if they are running parallel. That physical configuration maximizes it. So if you avoid that, then you typically can get away with it. And so if you analyze this, you can see the signal wires run this way, and the power wires generally run this way. They may be a slight angle, but they're crossing. So with that, then you're generally okay. So you can mix them if you know what you're doing. It's not that hard. So if you guys are helping lay it out, then I'll review your work and make sure, yeah, it's going to be okay. Let's see. Construction techniques. Down a bit. We're going to go over doing some crimping. I think at the Bechtel thing, some of you got to try one. So I've got a bunch of wires. Awty has some tools. I brought some tools, and all try it. I've also borrowed something from work. This is like what I brought the other time to Bechtel, but this is a nicer one. They built another one. The wood was all kind of had slivers and stuff. So these are examples of good connections and bad connections. So you normally would not need wire this big. I think the biggest we use is this size, but it's, yeah, so there's different things that are wrong with these, and you can talk about it, but there's nothing like showing you an example, okay?
That's a really good idea.
So there's all these examples of good and bad. And then we have connections that are like this on some of the motor controllers. And then there's times when you'll put bare wires in and without a lug. And this one, let's see. Yeah. You see how under the screw there's a little plate? You can actually put two wires in. One on, you'll have the little plate, and then there's a screw. You can put a wire on either side of the screw. But they need to be the same size or very similar. You can put a 16 and a 14 gauge. You know. Oh, real quick one. Talking about construction, there's different wire sizes. And in the rules, they talk about what sizes are allowed to be used on what kind of circuits. And they'll refer to the wire gauge. And so if you look at this bit of wire, there's all kinds of stuff printed on it. And somewhere in there, I know this is 12 gauge, you'll see 12 AWG for American wire gauge. And it's a little bit non-intuitive. The bigger, the larger the wire, the larger the conductor cross-sectional area, the smaller the number. And I think their gauge is something, say it's a 1-inch diameter hole, then if you're putting bigger wires in, you'll get fewer. And then like this stuff, I think is 22 gauge. You'll obviously fit more of these in a 1-inch hole than this. That's how I think of it. I don't know what the history actually is, but it correlates with that. So the metric system, they go by square millimeter. So it's really obvious what's the bigger wire. So be careful, because one team we used to be with, they spent most of the Thursday rewiring the robot because they had either used the wrong colored wires or the wrong sizes of wires. Either way, I don't recall. That's years ago.
Is the color like a rule, or is it just like preferred to have?
Some of them are rules, and so you need to read the rules for that year. But you can read, the latest rules. And you'll probably, I've not seen those rules change from year to year, but there's no guarantee they won't. But I've not seen it happen. Hypothetically it can, but it's good. They'll probably stay the same. So you'll get a very, very good idea of what to expect if you read, for next year, if you read this year's rules on that stuff. And then also the wire sizes for different circuits. So,
What is it?
this is an old voltage regulator module.
Okay.
So, okay. So a lot of it is use the right tools, use the right techniques, and check your work. Okay. So those are different cutters. You guys at Awty, if you have wire cutters like this or wire strippers like this, put it away. Tell Paul, just put it away. Because these things, there's a little screw here and it slides on this slot, and that's how you adjust how wide those jaws are for different wire sizes. I've got some of those and they're never at the right size. And if you close them on wires that are too big for how it's set, you start nicking the conductors. Okay? You start damaging them. And the nicer ones are like, and you just squeeze it and ka-chunk, it does it. So I think you may have tried it. It's way nice. And then, so here's some examples. Here's a good wire. Here's a really bad wire. It doesn't show up real well. If you looked on screen, you would see in this area, it's kind of copper color. The wires that we use are typically tinned, so they look silver, but it's really copper underneath. They put some sort of tin plating. So if you're seeing copper color, it means that your strippers are going past the insulation and into the metal, which isn't good. You should go up one size. Like the cutters are usually sharp jaws that do this, and they really don't need to cut all the way through the insulation. And then when you pull, it just rips it off. So here, some of the strands were damaged and ended up too short. The wire was cut at an angle to begin with. You know, there's all kinds of stuff wrong with that. So if you have something like that, cut it off and redo it. Because something like that, it won't crimp very nicely. You're just going to be wasting your time. The crimp lugs, you'll notice these ones with insulation, there's 3 different colors. Oh, okay. So red is for the very small wires, and then blue is for the medium, what we would call medium-sized wires, and then for our larger power connections, we'd be using the yellow ones. And so, and then these lugs, you see there's different types. These are called forks. These are rings. This is a fork. These ones, you notice, it looks like it bulges out. So when you stick it into something like this with a screw, these are meant for a certain size screw, and it'll go click. So when you're assembling this, you'll really appreciate it, because you'll go click, 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 and then you go and screw it down, and it holds itself in place. So if you're assembling it, yeah, it's a little bit tough. Well, just push a bit harder, okay? Let's see. And then you can put more than one of these lugs together by doing that, or you see how they're back to back on this one. So this, you have to have lots of space this way. You might not be able to put 2 on this guy, because then they'll crash into this guy. But you could do this. Well, you can't really do that here because this screw is too far in from the edge, so this guy wouldn't work. But usually we don't need to do things like that. Crimping. If you guys from Awty have one like this, throw it away. Those are horrible for crimping.
We died.
These things are designed so that when you put the proper range of wire in it, this barrel crushes the appropriate amount to make a tight mechanical and electrical connection. Now, I'll show you in a moment the ratcheting crimpers. But so when you look at this wire, the other end of it is labeled the same. Okay? So I was talking about serviceability. Because we labeled both ends, when we installed it, you can see how that makes troubleshooting way easy. Okay. What we did in the robot was the motor we labeled right front, RF. The wires, the connectors, everything got labeled RF all the way back. Okay, so we used a lot of R. There's also RR for right rear. So we ran out of R's in those booklets. We had to buy more booklets just for the R's. Okay, and the rest of the letters and numbers get hardly ever used. So we're going to just go with that. And at work, they've gone to not this brand, but something like that.
Where did you buy that?
Let's go and try and do some crimping and stuff. Let me just get this out of the way. This is your stripper, okay? So you put this one adjusts automatically. These ones you have to look what size and you put it in the right notches. This one, these are the jaws that cut it, and they adjust to a certain thickness of insulation. So you put it in. That thing is the stop, and you just go like that. You just, yeah. So he was saying that, yeah, okay. So there's two 14. This is, if you read this is 14 gauge. There's a 14 there and a 14 there. So generally towards the middle is bigger. So you see how that comes down, cuts the insulation, those come down, grab the wire, and pull it off. So I would tend to go for the bigger. Okay. Now conversely,
You already broke it. Just pull.
No, I mean.
Okay. Now try using this.
So like the
So you should, the scrap on this should go on this side. So this is the 14. You go like that and then you pull it off. Cycle it? Okay. Typically you want it lined up. This flat part, you want it like this. Okay, guys, when you're crimping, here's a trick, because they were messing around. They're using 3 hands to do it, 4 hands to do it, and that's how I did it too the first few times until I figured this out. Okay, when you align the lug with this, I think he's got it. Zach, align it so the flat part of it is along like this. Okay, don't do it like that. Okay, it just works out a lot better. Okay. Because it'll flatten, you see how these things are kind of flattened? When you install it, if it's flattened this way, it doesn't sit very well. So go like this, go click it like 1 click. Okay. Now, do you really need his help to stick the wire in anymore? No, right? So once you go one, it depends on the crimper and the lug, 1 or 2 clicks, and then it holds it firmly, but it hasn't really started to compress it. And then, and what you might want to do is do this. No, go, if your hands aren't strong enough, go like this, stand up, and lean on this thing. Lean, go like this and put your pressure on this. Without your phone there. And you still have to wrap your fingers around it to control it. Yeah, there you go. Okay, let's see. This one? So did you do a pull test? So you want to pull like that. It shouldn't come off. Now you don't need to pull quite that hard. But when you do the pull test, you're not going to use the same pulling force on wire like this as really thick wire, because you'll just break that wire.
Red wire on here.
Okay. Has everybody been able to crimp some successfully?
I hope so.
Okay.
Not very well, but yeah.
What do yours look like? Okay.
Amazing.
How are yours?
Average.
Okay. So you see how this one, it's crimped out here? This is really, in here is really the section that is supposed to crimp the wire, that is crushed down on the wire.
So like I should do it like the other one.
Yeah. So, yeah. Nick? You see, this is what's inside. So you've crushed down this part, so you've only crushed like the very tail end of this. So you're not getting the full holding power.